All right, guys, in this video we're going to talk about, as you can see here, a special case of the constant acceleration model. Maybe I should just pause for a moment and make sure that you guys understand what I mean when I write CAM. That's the constant acceleration model, just like CVM was the constant velocity model. So we're going to look at a special case. I mentioned in one of the videos that while we're thinking about constant or uniform acceleration, when I say uniform acceleration, that just means constant, as in the value isn't changing. In this course, that's the kind of acceleration we're going to be considering, but there are plenty of cases where the acceleration is non-uniform, meaning it's not constant, meaning the velocity, or the value of the acceleration changes. But I want to take a look today at a special case where it is uniform, and that is what's called free fall. So maybe I'll try to highlight this as special by making it a bigger font. Free fall. This is an important special case. There are other cases of constant acceleration, although they're not that easy to find, to be honest with you. But this is a very common and special case. So you guys know what it means to fall. Obviously, what does it mean to fall freely? What's the free part? In other words, if I say that something is in free fall, what exactly is it free of? And the thing that's free of, and you might already be guessing this, is it's free from air resistance. So free from air resistance. Now you might ask yourself, is this a fair assumption? In the real world, do I often drop things and find that they don't encounter any air resistance? And your answer, I hope, is no. The world that you live in, hopefully for the entirety of your life, will have air in it, which means that this model of free fall, of objects falling freely, is not necessarily a model that's a fair assumption under all cases. There are some cases, in fact many cases, where you can kind of ignore air resistance. So sometimes we can ignore air resistance. There are other cases where it's not fair to ignore air resistance, and maybe we can talk about when it's fair to ignore air resistance and when it's maybe not fair to ignore air resistance. But in this course, by and large, almost for the entirety of the year, we are going to be ignoring air resistance. So if you do that, if you imagine that there's no air and you were to drop something, you would find that it accelerates at a constant rate. So maybe we can kind of go into this without acceleration. If there's no air resistance, the acceleration of a dropped object is constant or uniform. And you might ask yourself, well, what is the acceleration? Is it 1 meter per second per second? Is it 2 meters per second per second? Is it 1,000,000 meters per second per second? What is it? I'm not going to give you in this video the exact precise value for the acceleration that a dropped object experiences. I'm going to give you a rough value. And then in class, we'll do an activity, a series of labs to try to figure out what is the precise value of the acceleration. I will say, though, that it's important enough that it gets its own name. This is, and again, I'm going to highlight this as important by giving it a bigger font. Its name is little g, or what's known as the acceleration due to gravity. Of course, if you drop an object, it falls because of this thing called gravity. So little g, is the acceleration due to gravity. This is an important point. So from this point forward, anytime I write little g, anytime you see little g appearing, that's an indication that we're talking about it's a free fall acceleration, the acceleration without air resistance of a dropped object. And I'm just going to tell you right now that on Earth, little g has a value of about 10 meters per second squared. About 10 meters per second which is actually, for everyday standards, that's pretty fast. In fact, it's really quite fast. If you were to get into a sports car and hit the gas and try to speed up as fast as you could in that sports car, there are not many sports cars in the world that can achieve this level of acceleration. So it's a pretty significant acceleration. To put it in terms of miles per hour, this is equal to about 22 miles per hour per second. So that means that if you were to have this acceleration of g, if you were to jump off of, imagine like a really, really, really tall building, it would have to be ridiculously tall, but a really tall building, and there's no air resistance, and you stepped off and you fell for 3 seconds. At the end of 3 seconds, you'd be going 3 times this, or 66 miles an hour, which is, that's really, really fast to go from 0 to 66 miles an hour in only 3 seconds. So it's a pretty big acceleration. What this means, by the way, is now since this is a uniform acceleration, I can plug this value, 10, this g is an acceleration, so I could plug in 10 as my a value for the big four. So in any of the big four, if I have an object that's dropped, that's falling, I automatically know that the acceleration is 10. Anytime I am dealing with dropped objects, I can use 10 for A in the big four. And you'll do plenty of calculations like that. Maybe just to come back to a velocity time graph, since we've talked about those, let's imagine what this would look like on a velocity time graph. So let's say I have a velocity time graph here, and I want to graph the motion of a dropped object. So perhaps, for instance, maybe we're going to put you, maybe we're going to put you on the top of a cliff. Here's a cliff. And here's you. There you are. Woo. And you're going to drop this rock, and it's going to fall. So we're going to say its initial velocity, maybe I'll go back to, I'll write it this way. V initial is 0, and you just drop it, and down it's going to go. It's going to accelerate downward. So the acceleration here is 10. Maybe one thing I'll note right now, this is not essential that you do this, but I will almost always, and this is important enough that I'll make a note of it. And in fact most textbooks, choose to call down, sorry, I want to do this in pen, down, we choose to call down is the negative direction, and up is the positive direction. So if I do that, then very, very often in this course, when we're writing A, when we're writing G, I'm going to choose to make it a negative value. So you'll often see me put the negative out front, just to indicate that I know that when an object accelerates due to gravity, accelerates downward or in the negative direction. So again, back over to here, that means that I can make this acceleration negative 10. Well, what would that look like on a velocity time graph? Well, the initial velocity here is 0, so that means I have to start here, right? At t equals 0, the velocity is 0, so I have to start at the origin. The acceleration is a negative value, so that means the slope of my line needs to be negative, and it's constant, so the slope should be straight. So it should look something like this, where the slope of this line is equal to negative 10, because the acceleration is the slope, remember, on the velocity time graph. All right, well, what would this mean? Can you imagine what this would mean? Maybe we'll try to do the opposite. What if I had this? I'll give you now the velocity time graph. So maybe I'll say here's a velocity time graph, velocity time, and I'm just going to draw this for you. We'll imagine an object that's in free fall. What would it mean if I told you the object's in free fall and the velocity time graph looks like this? I'm just going to sketch a graph, and I want you to think about what would a real world situation be for this. So maybe you can pause the video if you like and try to think about a real world situation where an object is in free fall and the graph of the object, the velocity time graph, looks like this. All right, so let's think it through, and then maybe we can try to figure out a real-world situation. Well, what does this mean? What we're told here, if I look, is I'm going to use this arrow right here. What does that mean? Well, that means right here the velocity starts with a positive value, right? All of these values up here are positive, right? Anytime I'm above the 0 point, these are positive velocities. And anytime I'm below the 0 point, these are negative velocities. So I'm starting, in other words, here with a positive velocity, which means up, right? Positive velocity, as we noted before, means up. So this means up, and negative velocity means down. So it starts with an up velocity, and that velocity goes to 0. So 0 means it's not moving, right? It's stopped right here. And then it goes into negative velocity, which means it's going down. So I have an object that's going up for a period of time, then it stops, and then it goes down. So I think it doesn't require a huge amount of imagination to think about what sort of situation could lead to that. I could imagine here maybe a scenario where I'm on the ground. Here's the ground, here I am on the ground, and I pick up a ball, and rather than dropping it, I throw it up in the air with some initial velocity. So it has some v initial. And then that ball, what's it going to do? Or that rock, whatever this object is, it's going to go up, 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 and then eventually it stops. The v is 0 at the very, very top. For an instant, it stops. And then what's it going to do? Now, maybe I'll just indicate it's going down. I'll use another color. Now it's going to go down, 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 and end up down here at some v final. So in terms of my graph, my v initial, this was the v initial. That's this that I threw it with, and then this v final would be whatever this is right here. That's my v final. So this would be an example. Now, one thing to note here, note that the slope of this line, once again, the slope of this line is a constant value. A is a constant value. And as we noted, it's going to be about -10. That's going to be the constant acceleration value due to the fact that that line is straight with a negative slope. One thing that might be worth pointing out, and this often confuses students, this point right here is the top of the path that the ball took. And at this point, that's this point up here, what do we know about this point? At this point, well, the velocity is 0. Here's the mistake that I find students and just people in general often make. They say, okay, the velocity is 0, it stopped, and they conclude then that the acceleration should be 0 as well. That's what they think. This is false. No, wrong. The acceleration is not 0. If I take a look right here, the slope right here is still -10. The slope right here is still -10. So even though the velocity is 0, the acceleration is not 0. The acceleration at this point is still -10. And it might be, if that seems weird to you, it might be worth thinking about what would happen if the acceleration were 0. If at the very, very top of the object's path, if the acceleration were 0 as well, what would that mean? It would mean that the velocity of the object is 0, meaning it stopped, and it's not changing. If the acceleration is 0, the velocity is not changing. So an object with 0 and unchanging velocity would be an object that just floats there in space. Obviously, if I throw a ball up, it doesn't stop at the top and float there. It comes back down, meaning it's accelerating still. All right, I think that's enough for now. Maybe we can do more practice with graphs in the next video.